All right, let's dive straight into this explainer and demystify exactly how to master logic statements for Cambridge AS and A-level computer science. Now, if you're studying for the 9618 syllabus, you already know that designing algorithm solutions is a massive part of the curriculum. But honestly, there is a hidden layer to mastering this that a lot of people miss. It's really not just about knowing your ands, ors, and nots. It is entirely about knowing how the person grading your paper actually evaluates your logic. So today, we are opening up the examiner's playbook. We're going to look directly at the theoretical foundations, the technical methodologies, and the specific examiner insights that literally separate an average grade from an absolutely exceptional one. Let's get into it.
So let's start with a big question that senior examiners bring up all the time. Why do students find applying logical concepts to unfamiliar contexts so incredibly hard? I mean, think about it. You've studied the logic gates, you know the Boolean algebra inside and out, but the second you're faced with a brand new scenario on an exam paper, everything just kind of freezes up. Well, most students lose easy marks here not because they don't know the theory. Not at all. It's because they struggle to bridge the gap between academic knowledge and practical exam execution. It's the application to an unfamiliar context that trips you up. You are basically tasked with taking this abstract, perfect concept and applying it to a messy, real-world problem. And that is exactly what we are going to fix today.
To secure those top marks, we're going to use this roadmap to deconstruct the exact method mark strategy examiners use to grade your papers. We'll cover the core assessment principles, move into the procedural framework, look at principal examiner warnings, and finish up with the evaluative thinking strategy.
Starting with Section 1, Core Assessment Principles. Basically, the rules of the game.
There is a huge direct insight here into the academic benchmarks. The quote says, "The assessment framework prioritizes analytical depth over superficial breadth." What does that actually mean for you? It means academic benchmarks require logical, structured reasoning rather than just writing down everything you've ever learned. A lot of candidates fall into the trap of doing what I like to call a brain dump. You know the feeling. You see a question about algorithm solutions and you just write down every single logic statement rule you've ever memorized. But the examiner isn't looking for a Wikipedia page. They're looking for analytical depth. They want to see that you understand the precise logic required for this specific problem, articulated with structured, clear reasoning.
To actually achieve that depth, examiners are actively targeting three distinct cognitive domains. We've got knowledge and understanding, application of concepts, and rigorous analysis. This means how you solve the problem is just as important as the final answer you arrive at. It is the core of the method mark strategy. You get rewarded for the process. If you just jump straight to a conclusion without showing your logical, structured reasoning, you are literally leaving precious marks on the table. You need to show that you know the concept, show that you can apply it to the scenario, and show that you can analyze the final outcome.
Let's move to Section 2, the procedural framework. Consider this your toolkit for systematic processing.
Okay, so there is a highly standardized sequence you must follow to guarantee you are picking up every available method mark. It's a 5-step process. First, identify the key elements of the problem. Second, apply the relevant principles. Ask yourself, which logic statements actually make sense here? Third, execute your analysis with clear working. Please, do not skip steps in your head. Put them down on the paper. Fourth, verify your results. Does this logic actually solve the scenario? And fifth, present your solution in the appropriate format requested by the examiner. If you stick to this exact sequence, you make it incredibly easy for the examiner to award you points at every single stage of your thinking.
Now, when we apply this directly to algorithmic thinking, you need to execute a very specific 4-step process. You're looking at step-by-step decomposition, appropriate data structure selection, efficient code implementation, and rigorous testing. This is your technical methodology, and it goes hand in hand with data interpretation skills. The framework actually demands that you can extract data from binary representations, perform calculations, and draw evidence-based conclusions. Think about it. If your logic statements are absolutely flawless, but your data structure selection is totally inappropriate for the context, the whole algorithm solution fails, and for sure your marks will reflect that.
Let's jump to Section 3, Principal Examiner Warnings. These are the specific pitfalls costing you marks. Listen closely, because according to direct data pulled straight from Cambridge Principal Examiner reports, candidates consistently throw away easy marks in 3 specific ways. First up, forgetting to check overflow and edge cases. That means failing to consider what happens when a computed value exceeds the system's maximum storage limits, or how the program handles the absolute extreme ends of expected inputs. Second, ignoring boundary conditions. How does the logic hold up at the exact threshold between 2 different outcomes?
For instance, what happens exactly at 0 rather than just slightly above or below it? And third, and this is a big one, providing answers that are completely detached from the specific context given in the question. That last one is a massive pitfall. If the question is about a temperature control system in a greenhouse, your logic statements and your explanation need to explicitly refer to temperatures and sensors, not just abstract variables like X and Y. You must ground your logic in the reality of the question. Your algorithm might work perfectly in the middle of a dataset, but examiners always check the boundaries, and so should you.
Have you ever lost a mark because you fully understood a concept but just used the wrong word? It's so frustrating. Well, examiners issue a massive warning here. Candidates constantly confuse key terminology. You might know exactly what you mean in your head, but if you write down the wrong term, the examiner literally cannot give you the mark. So the explicit requirement here is to clearly establish the meaning of terminology before you use it in extended responses. Use a memory hack, maybe a mnemonic using the first letters of key terms to remember exactly what each technical term means. Define your terms clearly right out of the gate. It shows confidence, it demonstrates that first cognitive domain of knowledge and understanding, and it completely anchors the rest of your logical reasoning.
Finally, we have Section 4, Evaluative Thinking Strategy. This is the winning strategy for critical analysis. There is a stark, undeniable difference between an average candidate and a top-scoring one. Standard answers just state a single solution. They find a logic path that works, they write it down, and they move on. But top-tier critical analysis demands so much more than that. Top-scoring candidates demonstrate evaluative thinking by considering multiple alternative solutions. They don't just find an answer, they are searching for the best answer. They analyze the trade-offs of different approaches, they openly acknowledge the limitations of their own logic statements, and they justify every single decision with hard evidence from the given scenario. This is exactly what unlocks those highest grade boundaries. So how do you actually do that under the pressure of exam conditions? Well, this is the ultimate deconstruct, solve, evaluate loop you absolutely must utilize to elevate your answers from just good to exceptional. First, identify the given information. Second, break the problem down into logical steps. Third, solve it systematically using the principles we just discussed. Fourth, and do not skip this, check for reasonableness. Does your algorithm solution actually make sense in the real world? And fifth, make justified recommendations. Compare your approach to the alternatives and explain exactly why your logic statements provide the optimal algorithm solution. This loop right here, it covers every single cognitive domain the examiner is testing.
So what does this all mean for you? The crucial takeaway is this: knowing your logic statements is literally only half the battle. The other half is presenting that knowledge through a rigorous, analytical framework. Remember to practice this specific deconstruct, solve, evaluate framework on your past papers. Relentlessly check your boundary conditions and edge cases, and always ground your logic in the provided context. When you sit down for your next test, don't just approach your algorithm solution like a student trying to recite a textbook. Approach it like a true examiner. Think about the method marks, structure your reasoning, and justify your choices. How will you evaluate the trade-offs in your next complex algorithm? Keep that strategy in mind, and you will be well on your way to mastering this absolutely crucial aspect of computer science.